I did some of the early ports of the Extend client to C++, and then also spent time leading the Coherence Incubator team where we focused on really very cool design patterns, including WAN replication, messaging patterns, processing patterns, and now I run the Fabric team at Workday, where we're taking and applying these distributed computing techniques to the Workday architecture and helping it scale. So why are we here? As I sat down to do this talk and think about this talk, I couldn't help but pull in Leslie Lamport's quote here, right? A distributed system is one in which the failure of a computer you didn't even know existed can render your computer unusable. Now let's stop and think about that for a minute, right? I mean, for us, the systems we're building are mission-critical systems, and most of them are distributed in some nature, right? So the fact is that you can have one machine, one thing go wrong, and you can bring the entire thing to a grinding halt, right? So one of the things that I think is important to talk about is, well, how do we mitigate that risk? How do we actually approach our development and our design patterns, and how do we ensure that we are testing as we go? So I want to start by talking about sort of my arc and the story that I continue to tell every time I move in my career about fabrics and distributed systems, right? If you think about what we're promising, the holy grail here is reliability, availability, scalability, and performance, right? I want to be able to get answers to my questions when I ask for them. I want the system to be up and running and available at all times. As load increases, whether it's questions coming in or memory that I need to hold on to, I need to be able to scale out my platform, and it has to perform, right? I can't tell you how many times in my career I've said, oh, come on, let's just build a system where we can throw hardware at the problem. Hardware is so much easier than engineering problems and writing software to solve a problem. The problem here is, though, it's a paradigm shift, right? As you start to embrace these distributed computing techniques, you have to start thinking about things in a completely different way, right? It's not about physical location anymore. And this is the first question that always comes up, right? I know my data, it's on this machine over here. I want to target everything to this machine. And the minute that you start thinking about locality with respect to it being on a physical place, you've completely hamstringed your ability to scale out an architecture. So you have to think about it in terms of partitions and relationships to partitions. And those partitions could be anywhere, not on a specific machine. And your data is highly available, right? Now, highly available is a great selling point, right? I can lose a node, I cannot lose any data, but it comes with complexity, it comes with a cost, right? What happens when things go wrong, right? How is my data highly available? What happens, if I lose a node in the middle of a write? When do I have to think about the idempotency of my operations? Right, so these are sort of fundamental tenets to building a distributed architecture from the ground up. Right? We heard earlier in the keynotes that it's very difficult sometimes to take an existing architecture and move them over to these platforms. Well, as you do that, you have to start embracing these techniques and these approaches. Right? And once you've got the fundamental basics in place, now we can start talking about, hey, let's execute code where the data lives. Right? That's another level of complexity. Right? Let's start talking about event-driven architectures. Let's respond to state changes and ripple that through the system and change behaviors based on state changes in the system. And finally, can we process our questions, our queries parallel? Can we use lock-free parallel algorithms versus procedural ACID-based, hey, let me pull everything to the client, let's grab a lock, let's do some mutation, let's push it back in. These are all sort of added complexity to the applications that you're building. And it's really important as you're building these applications to know the rules of physics for your system, right? What are the semantics around the eventing model? What are the semantics around when an entry processor or the equivalent is running and there's a failure? When is it retried? When do you have to, as a client, know to retry? And it's different depending on the systems that you're working with. So in order to really get down to the heart of the matter, I think it's important to sort of go back to the notion of CAP theorem. Because in any of the systems that at least I think about and my team thinks about, it's distributed on a network. And so CAP theorem says, in a distributed system, you can only have 2 out of the following guarantees across consecutive read and write operations. You can have consistency, where a read is guaranteed to return the most the most recent write for a given client. You can have availability where a non-failing node will return a reasonable response with a reasonable amount of time. Or you can have partition tolerance, which is the system will continue to function when the network partitions occur, right? So my buddy Jay says this is what we like to call the you can't have your distributed cake and eat it too theorem, right? You can't have it all. You have to pick a sacrifice somewhere. And it's actually not as easy a decision as you think, because the reality is the network is unreliable. It's always going to be unreliable. And so if you're building your application and you're testing on your laptop or you're testing in your little rack in the closet somewhere, you know what? Things are going to work great. And all of these systems work great in those conditions, right? What happens when things go wrong? You have to assume that the network isn't going to be reliable. And if that's the case, then you really only have two options, right? You can choose a CP system, things like Ignite are CP, or you can have an availability partition tolerance system. But you can't get rid of partition tolerance in a distributed system if you want to actually have it run in the real world. So all this comes down to thinking about, I think about things going wrong a lot, right? So I love Michael Scott. I'm not superstitious, but I'm a little stitious. What could possibly go wrong, right? I made this list in less than a few minutes as I was putting the slide together. I'm sure if we took a poll around the room, we could make a list 2 or 3 times this long, right? You could have, your nodes going into GC if you're dealing with Java, right? And going into GC once might be fine, but what if you've under-provisioned memory for the JVM and you're continually going into GC, right? In a distributed system, your system is only as fast as its slowest member, right? So you could have a node deadlock. I make some re-entrant call in my application that's running server-side. I didn't know that I was going to be burning the same threads that are processing requests, right? You could have reentrancy problems where the node's deadlock, right? It goes back to understanding the rules of physics of the system that you're working with. You could lose a node, right? Processes die, right? You could lose a whole machine. Network failures, there's a slew of great stories about network failures and what can go wrong. But it's not just failures, right? You could saturate the network, right? You could just have packet loss. You could have the network just not having enough bandwidth left for your application. And then there's the whole class of over-provisioned, right? You can over-provision a bare metal box. You go into virtualization, you start talking about Docker. Over-provisioning becomes more and more something I worry about, right? Because now you've got additional layers of abstraction on top of your application architecture, and there are unintended consequences, right? We've gotten really good at sharing memory on a box and sharing cores on a box, but usually you only have 1 or 2 network cards, right? So all of these things are things that you want to keep in mind and think about. And so you want these things built into your application design, your application architecture. One of my favorite quotes from a mentor of mine is, you can't sprinkle sort of scalable and performance into your architecture like you do salt in a meal. It has to be built from the ground up with these things in mind, right? So what can we do about that, right? What can we do to sort of make this a part of our culture as we're building distributed systems, right? So as we sat down and started thinking about this at Workday, we proposed a challenge, right? I want to develop a multi-process test suite where a single test can start and stop multiple nodes deterministically. I want to be able to run the same tests that my developers run on a laptop in a server farm somewhere where I can run it at scale, right? I want to be able to load test things, right? I want to be able to build micro benchmarks and reuse them. And finally, I want to be able to throw some chaos at the system, right? So this was the challenge we set out to build. These are the sort of techniques that I'm going to be sharing with you all at a high level. And to get to a system that works like this, there are some atomic building blocks that we want to start to include in our design. And the first one is something that we called an eventual assertion, right? The idea here is, when you're testing in a distributed system, the answers you want are not necessarily there right when you want them, right? Just simple process lifecycle, right? I start a process. I can't just throw a load at it, right? The process has got to boot. It's got to load the resources it needs in order to run, right? So I may want to wait for a process to start. So what we did with an eventual assertion is we said, I want to test that this condition is true within some timeout. And if it's true within that timeout, great. The conditions that I need for testing or moving on to the next phase of my test are good. Otherwise, something's wrong. Let's fail out and fail fast, right? So the idea is you test within a timeout, but also you have to keep in mind that some things you're testing, they might be actually sort of expensive. They might tax the system. So rather than just hammering the system and sleeping for 2 seconds at a time, we put an exponential back-off algorithm in there. So every time we wait a little bit longer and longer and longer so that we're not blowing the system out as it's trying to come up. And these things are really handy, right? I want to assert that my cluster is in a balanced state, right? If I'm building a system with a backup count of 1 and I'm dealing with an in-memory data grid, right? I want to know that my data is all actually in a safe state before I take some action, whether I'm testing or I'm patching the system. I want to know if a process is running, right? I'm doing some test, right? I want to know the process is running before I run my test. I want to know if I'm building a services architecture, right? And I'm deploying services to a distributed system. I may want to know that those services are deployed before I actually go take action and consume those services. So the notion of an eventual assertion is really handy. There are quite a few ways to approach it. We rolled our own. There's a library out there called Awaitility. It was referred to me about a week and a half ago. I've been meaning to go look at it in more detail. It looks pretty cool. And then the Oracle Bedrock project has an eventually construct in it as well that's pretty useful. The next topic, or the next component with respect to dealing with sort of testing your system, is you need process management, right? You need to be able to orchestrate your system. And I started out very early in my career building orchestration systems in my build systems, right? I had Ant, it would start up processes, then I could run my tests, then the processes would shut down, and there was a disconnect between the test code I'm writing and the actual orchestration of the environment that's my test is a part of. So, it's really important that there's a programmatic way to manage your processes, and that programmatic way to manage your processes is something that you can control from within your test. In addition, we really think about testing and trying to be purist about the real world. So we prefer multi-process testing in our environments. And this comes from just experience and doing this for a long time. There are definitely pros and cons to this approach, and I'm sure there are folks in the room that might feel that in-process, in JVM testing is really valuable. Love to have that debate with you at some point over the time we have here at the conference. For me, it's more about realistically representing things like the network, realistically representing things like having multiple machines and coordinating across multiple machines. Because no matter how hard I try to mimic that on my local machine, it's never going to actually match what happens in production. So I'd rather have a framework and invest the time up front to ensure that I have a reasonable way to manage and control my processes. I want to be able to run them locally and remotely. So what we've done is we've added the ability to sort of build and run Java processes on a local box, and we've actually extended that functionality to be able to run it remotely over SSH. So I can actually spin up as many nodes as I want on as many machines as I want, all through a very simple bit of code that I can then extend through configuration. This is another concept to think about, right? You don't want to have to change your code when you move from testing on a local laptop to testing in a remote farm, right? So you have to think about with your build system, how am I going to parameterize this? So the CI server can go, oh, I have 5 machines at my disposal. Let me actually configure the tests so that we can actually spin up and run those processes on all 5 machines. So thinking about extensibility over your code is really important. I think containers, AWS, they're both really valuable. I think containers is a new space. It offers sort of the same promise that we built locally for ourselves, where what you run on your local developer laptop matches what you're running in your remote machines. But the thing is if you go out to the container model, you lose the control of what you're doing inside of your test framework. So there's some extra work and spiking that we need to do to dig deeper there. And finally, AWS is a great place to do some testing. The fact that they have an SDN, the fact that they have the ability to sort of throw chaos both at the network as well as in terms of processes you're running, there's a lot of really cool stuff that you can do there. From a Java process management point of view, again, we rolled our own at Workday. if you go look at the Ignite project, they have added the ability to do some multi-JVM testing. So there's a grid abstract test, start grid and stop grid. Oracle Bedrock also has a runtime management system. I think I would highly encourage you all to look at these different approaches. I would encourage you to bring back to your development houses the importance of building out a system that sort of matches what happens in the real world. And the reason that we want these building blocks is not just because from a purist point of view, I want to be able to start and stop systems on a single machine or on remote machines, but it's so that I can start to build out real chaos in my tests, right? So, Netflix and the Simian Army and the Chaos Monkey, really inspirational stuff. I love the idea about killing machines and all of that. I think that's an important component when you start to take on the paradigm shift of distributed computing. You have to throw some chaos at your system, right? So we have a couple of simple algorithms that we've built that we apply to a bunch of our tests. And the first one is what we call the process monkey, right? The idea is you have a multi-threaded test where you have one thread that is responsible for running some comprehensive, concrete, deterministic operation against your fabric, right? Maybe I'm doing puts, whatever, something that you can verify easily. Then you have a second thread that's actually verifying it, right? So you have a reader and a writer thread. And to throw some chaos in the system, you add another thread that now can start killing nodes. This is where being able to programmatically control your system is really, really valuable, because now you can build this into an abstract concept and apply it to any test that you want to test, right? Concrete example for us, this was one of the first tests we wanted to write as we were building out our platform and our framework, and it's the aggregation test or the checksum test, right? So we have a writer thread, and it's just increasing monotonically, putting in monotonically increasing values, right? 1, 2, 3, 4, 5. The nice thing about that is it's really easy to figure out what the sum is if you know what the highest value you inserted in, which means that I can actually do a checksum, right? I can have my reader thread do a get all based on the highest value that's been written to the cluster, and I can actually then calculate the sum and compare it with the expected sum. And if they don't match, I've lost data, right? I've actually proven that the system is either partition tolerant or not. I've proven that the system is actually working as designed or not. But the thing is that when you're killing nodes randomly, you have to actually take account the limitations of your system, right? If I just stop and start nodes and I have a system that's limited to a backup count of 1, it will be completely unfair and unrealistic to expect that, if I kill 2 nodes, that I'm not going to lose any data, right? So one other concept you want to bring into the notion of sort of your chaos monkey is some sort of a predicate, some sort of a test, right? I want to know, as I mentioned earlier, I want to know my cluster's in a balanced state. So as I'm stopping and starting nodes, I can kill a node, right? And really destructively kill it, right? Not nicely with a clean shutdown, but like kill it, right? Kill the node, bring a node up, and then I can wait. And I can say, oh, I want to wait till my cluster's balanced. Well, we have that additional atomic building block of an eventual assertion, right? So now you can put in some reasonable sort of constraints around the type of chaos that you're throwing at the system. So this is a foundational element to how we approach testing our distributed systems and our distributed platform. There are areas we want to explore into, right? There are areas that I want to ensure that we also are covering, going back to being superstitious, right? I want to make sure that we're testing with some network chaos as well. The Simian Army, as I mentioned, has some very, very cool stuff in it. It's not just a chaos monkey for processes or for VMs. They actually have network monkeys as well. So I would like to see if we could take those concepts and apply it both in our AWS testing as well as in our local in-house environments as well. In addition to throwing chaos at the system, in addition to beating these systems up, I think it's also really valuable to be able to performance test what you're doing. And you want to be able to performance test deterministically and repeatably as well, right? And this gives you really a powerful way to have feedback as you're trying things out, right? Maybe I want to try, there's 3 different implementations of an atomic data structure, right? One that I've written myself, one that's provided by the vendor. I want to try them out, right? So I want to be able to benchmark them. Maybe I have some algorithm that I've implemented, right? And I want to be able to to tweak it, right, and get some deterministic feedback on what's going on. So we did a few things. We worked with a very old test framework, JMeter. I'm sure some of you are scratching your heads why that is. Well, sometimes you make the engineering decision to work with a platform that other folks in your organization are working with. One of the most valuable things that you can do as you're building these systems is make it easy for other people to consume and work with, right? So we worked with JMeter, we extended it, we created a JMeter unit test runner. So we actually extended JUnit and made our own runner that extends the life cycle to sort of line up with the life cycle of how JMeter works, right? The idea here is in our before and after classes, we're bringing up clusters, right? And we're shutting down clusters. Well, when you get to the point where you're doing some sort of a performance test, you want to bring the cluster up, you want to run some test m times over n threads, and then you want to get a throughput calculation, and then you want to bring the system down. So we changed the life cycle so that as a developer, you write the test once, and it can be a unit test, or it could be a performance test, depending on the needs at the time, right? We also had the pleasure of getting to partner with some other folks in the company and integrate all of this with a time series database. So JMeter, at the time we wrote this, actually writes out over the Graphite protocol, so we can put our throughput over Graphite into InfluxDB. And then we can use collectD on the systems to actually grab telemetry as we're testing, right? So now I can kick off a load test. I can actually send that data into a time series database. I can fire up Grafana, and I can see the results in real time as the test is running. What's even better, I can actually go back and look at the tests later and actually do historical comparisons as I go. So now I have a graphing system that allows me to see results as we improve or as we make things worse. It gives you another way of getting some real-world feedback as you're going. So where are we now in our process, right? So we have an internal test framework. We run it on every upgrade. We're working with Apache Ignite quite a bit. We're working with GridGain. So we run this every time we upgrade, and it has saved us a few times and allowed us to work with GridGain to make improvements in the system. And we want to give back to the community. So we've gone through the process at Workday to make sure that my team has the ability to contribute to open source projects. We've been in the process of creating our own fork and actually taking code that's written in our platform and applying it to the actual Ignite open source platform so that we can represent or recreate the same test frameworks like the Process Monkey I talked about before in there. And so you can expect at some point in the near future we'll hopefully get a pull request in and get that committed. We'll be spiking on the Network Monkey. That's sort of the next frontier for us as we build out our test framework. We've got good process chaos, so now I want to add some network chaos. And then the Fabric team, which is the team that I run here at Workday, is putting the easy button on distributed computing. So we're not doing this for just one or two use cases. We're building a platform for distributed computing at the company. We're building sort of Fabric as a service on the one hand, and we're also building sort of a platform and a runtime that makes it really easy for application developers to embrace these paradigm shifts. So we're exposing things in a way that's intuitive. We're working with those teams to make sure that they are applying best practices to this space, because it is a very painful thing to go from a sort of standard procedural in-process approach to a distributed approach. It's uncomfortable. And so the good news is that we have some experts that have gone through this process and can aid with that discomfort. So we happen to be hiring and growing out that org. So if you or anyone you know might have an interest in talking to me about that, that's also a possibility. In the context of full disclosure or sharing, I think there's a few recommended readings that I would suggest. The first is Kyle Kingsbury's blog. Out of curiosity, how many people in this room have heard of Kyle Kingsbury? A few. Okay. I highly recommend you check him out. Kyle Kingsbury focuses on braking systems in the context of CAP theorem. He's written a test framework in Clojure. I left it out on the other slides because I'm very Java focused. But he has broken everything from Cassandra to Zookeeper. He just is doing some really impressive stuff. I highly recommend it. Brewer's Conjecture, which is sort of the paper on CAP theorem, highly recommend you read that. Why you can't sacrifice the partition tolerance in a CAP system. And finally, the fallacies of distributed computing. It's a great read on Wikipedia. It won't take you long. Highly, highly recommend it. These are the things that I think shift your mindset when you're testing a system. You know, when you're building an architecture, you got to think about what can go wrong, and you've got to sort of plan for it. So I wanted to leave some room for a dialogue, whether you want to share some of your approaches to doing some distributed computing testing, or if you have questions about our approach and how we approach things. I thought I would leave some room at the end of the talk for sort of a dialogue and a question and answers session. Does anybody have questions or want to share a story about how they approach testing these types of technologies?
How much access do you need? For instance, if you use AWS, do you feel you'll have access to the framework and the network?
So the question was, how much access do you need? And if you're using AWS, do you have access to the network and the things you need? Did I get that right? So if you want to do simple process, multi-process testing, right? I tried to keep the framework very simple. I know my colleague Brian, who's over at Oracle, did the same thing. All you need is SSH access. Right? So if you can SSH to a box, you can start processes on a box. Right? Keep it really simple. So in the AWS world, which is where we wrote the first rounds of tests for this stuff, all we had to do is make sure that we could log on to those machines and that we could SSH between those machines. And that gave us the process piece. The networking piece is going to be a little bit trickier. Right? That's really very domain specific to your environment. Do you have an SDN? Right? Are you running OpenStack and you have access to some way of actually messing with the network? If not, it gets really hard, right? You've got to go through ops, you've got to deal with switches, maybe you need somebody to just pull a cable for you, right? That's really hard. I think that that's where the containers can come in really handy because you can actually start tweaking the network in that way. AWS is a different story. It is an SDN model. There's an API for tweaking the SDN, so you can do all sorts of really cool stuff. The Simian Army stuff actually does two things that I saw. It actually sort of changes the firewall rules locally on the boxes, as well as tweaking the SDN to prevent reachability between nodes. It's pretty neat stuff. Does that answer your question? Yeah. Michael?
So when you're doing performance testing on AWS, how repeatable?
So the question was, when you're doing performance testing on AWS, how repeatable do you find that to be? Part of my answer is going to be specific to the building blocks that we used, right? They're deterministic, they're repeatable. The big difference is that the results may not be the same from run to run in that you're working in a virtualized environment. Now, when we did our testing, we picked the sort of beefiest blades and we picked the beefiest networks. So there was less over-provisioning of the environment. We saw pretty consistent results because we weren't using small VMs. Very often, a lot of times, what we care about in the short term anyway, when we're evaluating things is relative performance. How does this particular thing compare to that particular thing? When we get into sort of the longer term stuff, we have been doing more in-house stuff and have a little more control over the provisioning there. It's a good question. Question from the back. So the question was, is there any particular workflow or orchestration tool that we leverage? At the moment, no. We've embedded all of that functionality into our unit tests, right? So we're starting processes and stopping processes through a library that we've built. We are spiking on and looking at some orchestration frameworks for sort of the next phase of our on-demand stuff. We're looking at Mesos, we're looking at Marathon, we're looking at Aurora, we're looking at Kubernetes with Docker. We're looking at all of those things, but we haven't actually started using them in any real way yet. And I think there is some promise in that. I think that the trick there is that orchestration frameworks, they all sort of solve part of the problem, but miss other parts, right? I haven't yet found a comprehensive solution to that. Okay, got it. So the question was more like, given the orchestration frameworks I talked about, are we leaving VMs up and sort of starting and stopping containers on the box? So I want to peel the onion back a little bit further for you, right? So right now, everything we've done is built in Java. So I don't use containers at all in my testing framework. I have what I call a Java process builder. And you can set the parameters that you want to set, and it's an extensible framework. So we have a fabric process builder that knows how to start Ignite, for example, and put the things on the class path that we care about. And we just use JCSH to open up an SSH connection to the remote machines, and then a simple sort of REST-based model where we serialize that local builder and deserialize it on the other side and run the processes out of that. So it's sort of an ingrown, in-house approach to the problem. And the reason for that was we started with local process testing, and I wanted to be able to take what I'm doing on my laptop and apply it to the remote systems. And I didn't want to have to worry about, hey, do I have Docker installed on those remote machines? I wanted to have a very simple, the VM's up, I can run some tests. Does that make sense? I think that's a direction that's worth exploring further. I think that the containers are here. There's a lot of mind share there. It's just we started with a very fundamental basic building block and sort of went from there. Excuse me, so the question was, how do you isolate the hardware with respect to the performance testing? And I'm going to sort of ask for a little more detail. What is your concern there? Are you worried that the hardware is over-provisioned and it's doing something else? What are you trying to isolate from? Over-provisioning of the hardware. Okay, so very often, so that's a function of I have a dedicated set of machines that are at my disposal, right? So I know what's been provisioned on them and I know what's running on them. I think that's an important component. If you're trying to do relative performance runs across time, you need a deterministically repeatable set of hardware to do that on. On the AWS side, I think what helped us there was, and AWS was pretty excited because we had used some of their advanced networking, right? We wanted to push the network and attack things. So they actually gave us a couple of extra high memory machines higher than above quota, so we could actually do that testing. And so I think that's where, for us, when we would do that, we would spin up a blade, right? We'd say, I want the whole thing so that I know I'm getting the whole thing and what its characteristics are. That's a good question. Any other questions? Okay. Well, thank you very much, everyone. Appreciate it.